Welcome everybody to the first public event of the LSE Mathematics Department in 2016. My name is Jantar Mantar. Heuvel. I'm one of the members of the faculty in the Department of Mathematics. Before I introduce the speaker, just a little bit of promotion for the department. For people who are following us on Twitter or following Twitter or like to live tweet this event, please use hashtag LSE Marts. And if you want to follow it, there is the @LSE Marts. That will also be the place you can find information and links and announcements of other things we organize. And in particular, the talk of today will be recorded and will be fairly soon available as a podcast and as a video online. And again, that will be announced via Twitter, but of course also on our website. So having said that, I think let's just get down to real business. It's my honor and very great pleasure to introduce a long-standing, I think I might say friend. I mean, definitely we know each other for quite a while. Professor Robin Wolfson, who's today's speaker. Robin has a long and distinguished career, did a PhD in mathematics at Pennsylvania, although he's British born and kind of lived for most of his life in this country. He has been working, he's now an emeritus professor from the Open University. He's an emeritus professor from Brahma College here in London. He's also a visiting professor of our department here at the LSE. And he teaches for us on the history of mathematics with great enthusiasm and with good in attracting students. Mathematically, he started, well, I think he scientifically started as working in graph theory, discrete mathematics, which is also my area. But more recently, most of his work, his research, his writing is about the history of mathematics. He's written about, when we're walking here, he told me he had written about 40 odd books on the topic, which is more than some of us publish in our articles. He has about 8 books in production in some stage. And if he gets bored, he will start looking at least 5 that are somewhere on the on the drawing board to be published in some time. Most of these books will be about certain aspects of history of mathematics. So let's kind of start listening to one of the kind of his expertise is the kind of the mathematics of non-Western civilization. So Robin, the floor is yours. Thank you.
Well, thank you, Jan, and thank you, good evening, and thank you all for coming. Today I want to look at the questions, where did our mathematics come from, and how did it originate? Undoubtedly, the earliest methods of counting included forming stones into piles, cutting notches in sticks, and counting on the fingers, which led eventually, of course, to our familiar decimal number system. And in several places we find geometrical arrangements of stones, such as the circular patterns at Stonehenge. But for today, I'd like to talk about the mathematics of the 5 cultures that you can see here, starting with Egypt and Mesopotamia, and then proceeding via China and India to the Mayans of Central America. These periods are shown on this timeline, and I'll be covering the 5 cultures shown in blue. So I'll start with Egypt and Mesopotamia. Greece needs a whole lecture to itself, that's for another day, while Islamic mathematics in Europe came later. So the second half of the lecture will be on China and India and on the Mayans. But before we start, I'd like to remind you about place value number systems. We use a decimal system, of course, that uses only the numbers 1 to 9, together with 0. But the value of a number depends on its place or position. So in the number 3139, the first 3 represents 3000, whereas the second one represents 30. But once we have a place value system, we can then calculate beg your pardon. Once we have a place value system, we can then calculate in columns. Units first, then tens, hundreds, thousands, and so on. But as we'll see today, not all of the cultures we'll meet today had decimal systems, and not all of them had a place value system. So we'll start our story today with Egypt and Mesopotamia, which are shown on this map. Ancient Egypt developed along the valley of the Nile, while Mesopotamia, as its name suggests, developed between two rivers, the Tigris and the Euphrates. And as we'll see, the primary sources, the surviving primary sources, are markedly different. We know relatively little about the Egyptian world because their writings were on papyrus, which rarely survives the ravages of the centuries. Only a handful of mathematical papyruses still exist, such as the Rhind papyrus in the British Museum, named after its Victorian buyer, Henry Rhind. It was written by a scribe such as the one shown above. On the other hand, Mesopotamian mathematics was imprinted on clay tablets that were baked in the sun, and many thousands of these have survived. Incidentally, what I call Mesopotamian mathematics is often referred to as Babylonian mathematics, even though it wasn't centered in Babylon. That term, incidentally, is now going out of use. When studying the mathematics of ancient Egypt, we're immediately struck with how little the subject changed over a period of 3,000 years. Egyptian society was centered on the River Nile, which irrigated the land so that crops could grow and cities could develop. The civilization was a hierarchical one, headed by the mighty kings and pharaohs. From about 2700 BC, the pharaohs desired to be buried in massive pyramids, and the oldest of these, King Joseph's step pyramid at Saqqara, which you can see above, was built in horizontal layers and was supposedly designed by Imhotep, the celebrated Grand Vizier and architect. But better known are the magnificent pyramids of Giza, which date from about 2600 BC and attest to the Egyptians' extremely accurate measuring skills. In particular, the Great Pyramid of Cheops in the middle has a square base whose sides of length 230 meters agree to within 1/100th of 1%. Constructed from over 2 million blocks, averaging about 2 tons in weight, and transported 50 miles by a whole army of workers, the pyramid is an impressive 146 meters high. Even more remarkable, it's not solid, but contains an intricate arrangement of carefully planned internal chambers and passageways. But how did the Egyptians count? Now, moving forward now to about 1850 BC. Like most counting systems, theirs was based on 10, but it used different symbols for 1, 10, 100, 1,000, and so on. A bit like Roman numerals, which had different symbols for these numbers, and they also, of course, had different symbols for 5 and 50 and so on. So what are the symbols here? There's a vertical rod for 1, a heel bone for 10, a coiled rope for 100, a lotus flower for 1,000, and so on. As I said, recall that the Romans similarly used different symbols for 1, 10, 100, and 1,000. A number is then represented with the appropriate number of each symbol written from right to left. So here's the way they wrote 2,000, 600, and 58. However, their fractions were very different from those that we use. Apart from 2/3, which was a frequent fraction, all their fractions were unit fractions or reciprocals, 1 over n. For example, 1 over 5 and 1 over 66 and so on. So, for example, where we would write 2 over 13, they would write something like, in fact, they actually used this one, 1 over 8, 1 over 52, 1 over 104. And if you actually add those together, you'll find you do get 2 over 13. How did they add? That's quite easy if you're adding whole numbers. Here are 367. You can see 3, 6, 7, and 756. 756. And to add them together, you just collect the symbols together. So you collect the ones together. There are, first of all, 7, and then there are 6, so that gives you 13. So that gives you 3 vertical rods and a heel bone. So now you look at the heel bones, which are 10, and you've got 6 here, plus the 5 there, plus the one you've carried over, and that's going to give you 12. That's going to give you 2 of those, and then a coiled rope. And you carry on in this way, and so you just start and you collect things together, move them over, and the adding is perfectly straightforward. Multiplication is more interesting. And it was done mainly by successive doubling and halving. They seem to be able to double and halve anything, and also, of course, multiplication by 10 is simple, because you just take each symbol and replace it by the next one. So here's how they multiplied 80 by 14. You first of all write 80 with a 1 next to it, and you can see the hieratic script there and our numbers on the right. And then you replace each heel bone by a coiled rope to get 800. That's the second row. Next, return to the 80 and double it. First to get 160, and then 320. And you notice that we've been keeping tabs on these things. So if you look at the right-hand side, you notice that I have marked the 10 and the 4 with a slash, okay? Because they add together to give 14. So if you want to multiply 80 by 14, it's 80 times 10 plus 80 times 4. So you just add those together, and that gives you the result that you can see down here, which is 1120. Now, the Rhine Papyrus actually had on it, it had tables of numbers of fractions. It had expressions in unit fractions for 2 over 5, 2 over 7, all the way up to 2 over 101. But most of the Rhine Papyrus and the other main papyrus, which is the Moscow Papyrus, consists of a number of problems. There are about 80 or 84 problems on the Rhine Papyrus. So here's number 25. The quantity and its half together become 16. What is the quantity? How would we do it? Well, in modern algebraic terminology, which of course they didn't have, we'd be solving the equation x plus a half x equals 16. 3 halves x equals 16. That would give us the answer x equals 10 and 2/3. But of course they did not have the algebra and the algebraic notation for doing such problems. So the method that they frequently used was the method of false position. Here they guessed a convenient solution and then scaled it up or down. Now you've got to add a quantity in its half, so a good guess to take would be 2. Because if you take that and its half, you get 3. They then scaled the 3 up to get 16 and said, and if you now apply the same scaling to 2, then you get the answer. And so that's what they do. Don't worry about all the details. So that's scaling. As many times as 3 must be multiplied to give 16, so many times 2 must be multiplied to give the required number. So you start off with 1 and 3, 2 and 6. They keep on doubling, and then how far do you double? Well, you've got 3, 6, 12. You don't want to go any further than that because that takes you beyond 16. So you've got 12. That's good. Then you go back to, you say 1 is 3, so 2/3 is 2, and 1/3 is 1. And now if you look at the 3 and the 12 and the 1, that's 16, that's what you want. And now you look at the corresponding things on the left with the slash marks against them, they give you 5 over 1/3, which corresponds to 1, and so what corresponds to 2 is 10 and 2/3, and that's your answer. So that's how they did that. And once you've seen a few of these, then it's not that difficult. And they incidentally then checked the answer. But their ability to calculate with these unit fractions was incredible. Because look at this one, this is problem 31. A quantity, its 2/3, its half, and its 1/7 added together become 33. What is the quantity? So we would solve x plus 2x over 3 plus x over 2 plus x over 7 equals 33. And if we do it right, we get 14 and 28 over 97. Well, they went through all this, and what's their answer? Look at that incredible, instead of 28 over 97, they got that incredible row of unit fractions. They really did know how to operate with these. And then they followed it with the nice line, which multiplied by 1 2/3 or half of 7 makes 33, clearly. So how did they do it? They used extensive tables of numbers, breaking fractions down into a succession of fractions of the form 2 over n, 2 over something, and which of course has appeared on the Rhine papyrus, and then they combined these repeatedly until they got the answer. A rather different sort of problem involves the area of a circle. Problem 50 asked the scribe to find the area of a circle of diameter 9. Now, they didn't say pi r squared or anything like that. What they did was they had a rule of thumb which enabled us to find approximately the area of a circle. And what they did, the rule was they used to reduce the diameter by 1/9, which is why this problem, which is a teaching problem, had a 9 in it, and then square the result. So you take away 1/9 of the diameter. This is the description on the papyrus. Take away 1/9 of the diameter, namely 1, and the remainder is 8. Multiply 8 by 8, it makes 64. Therefore, it contains 64 cetat. That's an area of a measurement of area, which is cetat of land. So the answer is 64. So in our modern algebraic notation, the area is got by squaring 8/9 of the diameter. And in terms of the radius, this is 256 over 81 r squared. 256 over 81, that corresponds to a value of pi of about 3.16, which was an excellent approximation for almost 4,000 years ago. Our last Egyptian problem from the Rhine papyrus is problem 79. It involves adding powers of 7. The papyrus lists houses 7, cats 49, rice 343, wheat 2,401, Hecat 16,807. It then proceeds to add them all up for no apparent reason whatsoever to give 19,607. So what it's doing is it's teaching the scribe how to add powers of 7. Now we've seen this before, have we? Does it seem familiar? Yes, as I was going to St. Ives, I met a man with 7 wives. Each wife had 7 cats, etc., etc. And it ends up how many were going to St. Ives. So again, most people in answering that would list the powers of 7 and then add them all together, giving the answer. Of course, it's the wrong answer because the answer is 1, because I was the only one that was going to St. Ives, but there we are. But it's amazing how this problem appeared later on in the problems of Fibonacci. Fibonacci had a book of problems, and again in our nursery rhyme. This example dramatically illustrates how the same mathematical idea can resurface in different guises over thousands of years. Let's now turn our attention to Mesopotamian mathematics. Although dating from the same time as the Rhine papyrus, their sources, clay tablets, were very different. Using a wedge-shaped stylus, they imprinted their symbols in the moist clay, as you can see. This is called cuneiform writing, and the tablet was then left dry in the sun. And as I said, we have thousands of mathematical tablets that have survived. Unlike the Egyptian counting system, however, which was a decimal system with different symbols representing the powers of 10, the Mesopotamian system was a place value system. But it was based on 60, and it used only 2 symbols, remnants of which survive in our measurement of time. 60 seconds in a minute, 60 minutes in an hour, and also angles, where you have 60 degrees, 360 degrees, and so on. However, there were ambiguities because the same succession of symbols, such as the one you can see on the right, might refer to 41 60s plus 40, or it might be 41 and then 40 60ths, or many other different things, depending on the context. Now, that may seem unsatisfactory to us, but this idea of context is quite natural for us. 650, that might represent time, meaning 10 to 7. Or the cost of a bus trip, £6.50. Or the cost of an airline flight, £650. And from the context, you know what someone's talking about. There are essentially three types of mathematical tablet. The first two are table texts, which listed tables of numbers that are used in calculations, and problem texts, which we'll see in a minute, in which problems are posed and solved. There's a third type, basically used for schoolwork, because if you were teaching a whole lot of kids, for example, and you had your clay tablet and they'd do a calculation with their cuneiform writing, if they got it wrong, they could always just rub their finger through it and then have another go. And quite a lot of these have survived. So we actually know quite a bit about the way they taught through these school tablets that have survived. Let's go back to the table text. Several of them represent multiplication tables. And here's the 9 times table. On the left, you have 1, 2, 3, 4, and so on, all the way down. Whereas on the right, you have 9, 1, 8, that's 18, 2, 7, 3, 6, 4, 5, 5, 4, and then 63. And remember, it's the same symbol for 60 as you had for 1. So that's an example of a 9 times multiplication table. These tablets, by the way, they're only this size. They're hand size. You can hold them in your hand. They're not big things like the Rosetta Stone. They're very, so they must have had exceedingly good eyesight. An example of a problem from a problem text is this one. I found a stone but did not weigh it. After I weighed out 6 times its weight, added 2 jin, which I hasten to add as a unit of weight, and then added 1/3 of 1/7 multiplied by 24, I weighed it, giving 1 mana, another unit of weight. What was the weight of the stone? Well, this problem is clearly not a practical one, because if you simply wanted the weight of the stone, why not just weigh it in the first place? It's actually one of 23 such problems, all on the same clay tablet, and all ending up with 1 mana, which leads us to believe that the tablet is a teaching tablet. And the person using it would know that 1 mana equals 60 jin, and then we can argue as follows, and this is using our modern algebraic notation, but they wouldn't do this. But the tablet actually does give the solution and the step-by-step solution. So with our algebraic notation, if x is the weight of the stone, then 6x plus 2, that's 6 times its weight plus 2 jin, plus 1/3 times 1/7 times 24 of it is 60 jin. Of it. Now, it doesn't mean of the weight of the stone. It means of the part of the calculation you've got to so far, which is 6x plus 2. So it's 6x plus 2 plus this proportion, not of the stone, but of the 6x plus 2, which we've reached so far. That's equals to 60, and if you solve it, you then get 4 1/3 jin as the answer. This had to be worked out from the context, because the tablet gives the answer, and it's only by working back from the answer that you can actually find out the details of the method. Now, this is an example of what we now call a linear equation. The Mesopotamians were also skilled at solving what we now call quadratic equations 4,000 years ago. And the amazing thing is their method, which I'm not going to show you today, but their method was completing the square, which is the same method we essentially use today. Quite remarkable, some of the problems that they were able to solve all that time ago. A particularly unusual and exciting tablet, this one is in the Yale Babylonian collection. It shows a square with 2 diagonals. And you can see the numbers 30, that refers to the side of the square, 1, 24, 51, 10. Now what that means 1 plus 24 sixtieths plus 51 over 60 squared plus 10 over 60 cubed. Well, if you write that all, if you work that all out in our decimals, you get 1.4142128. In other words, it's an extremely accurate value for the square root of 2. So the numbers that appear here, that's the square root of 2, and that's 30 times it, which is the length of the diagonal. And but to show how good this is, if you actually square the number they get, or the number that they gave, 1245110, you actually get 2 to within 5 parts in a million. Quite remarkable.
Is this the best possible with, I mean, like if this 11 would be 10 would be 11, it would be less accurate?
That would be less accurate, yes. Yeah.
So it's the best with these 3 digits?
That's right, yes. And that's amazing. Let's now turn to the mathematics of China and India. Around 250 BC in India, King Ashoka, his edicts were written on various pillars around the kingdom, and numerical information appeared on these pillars. King Ashoka was the first Buddhist monarch. These numbers were written in a place value system based on 10, using only the numbers 1, 2, 3, up to 9. And later on, 0 started to be used. So this seems to be the origin, as far as we can tell, of what we now call our Hindu-Arabic number system, with the separate columns that we use for units, tens, hundreds, and so on, as I showed you at the beginning. The Chinese had a similar scheme with their counting boards, in which there are separate compartments for units, tens, hundreds, and so on. This is interesting. If you look at Chinese writing at the time, they actually had a system a bit like the Egyptians, which wasn't a place value system, because they had different symbols for 1, 10, 100, and so on. But for their counting boards, they just had these symbols here. And basically, here you can see 1713 and 6036 as we write them. Notice there are only 9 different symbols, with 0 represented by an empty compartment. So you've got a box with different compartments, and you put in, here are the units, and here are the tens, and here are the hundreds, and so on. And you put in little bamboo rods to the appropriate number to indicate the various numbers. So if you want 1713, for example, the thing that's interesting is because if you use all the ones at the top, then some of these are going to look very much the same. So if you've got 5 ones in successive things, then they're going to look complicated. And so what they used to do is for each successive box, they would turn them round, either using the vertical symbol at the top or the horizontal one down below. So 1713, starting from the right, you've got 3 vertical ones for the 3, you've got a horizontal one for the 1, you've got the vertical 7, and then you've got the horizontal 1. You notice that the same symbol is used for 1 in both occasions. However, if you're looking at 6036, you start on the right with a vertical T, then you have a horizontal 3, a blank, an empty box for 0, and you have a vertical 6. So in this case, the 2 6s you have the 2 different forms, horizontal and vertical, appearing there. That's, as I said, so the calculator can distinguish more easily between adjacent compartments. In this context, it would have been natural to introduce a 0 symbol for an empty box, although the Chinese didn't do so. The Indians did, however, and whether they were familiar with Chinese counting boards is unknown, although the Chinese did visit India, and the boards were transportable like laptops, so it's quite possible. In any case, the Indian number system developed as a place value system based on 10, using only the numbers 1 to 9, unlike the Egyptian and Greek systems, and eventually, possibly around 400 AD or a little bit later, including also the number 0. Let's now look at the mathematical activities in China in more detail, although primary source material is very sketchy, since they wrote on bamboo strips, and later on paper, neither of which survives the centuries well. There's an ancient Chinese legend about the Emperor Yu. Now, we don't know when this was. It might be, say, about 1100 BC. So the Emperor Yu was standing on the banks of the River Lo, which was a tributary of the Yellow River, when a tortoise or a turtle emerged from the river with a pattern of numbers on its back. In fact, a 3x3 magic square. I'm not sure whether all turtles in that part of China have 3x3 magic squares on their back, but this one apparently did. There's a drawing of it. A 3x3 magic square, that's a square array of numbers that you can see there, in which the sum of the numbers in each row is 15. And the sum of the numbers in each column is 15. And the sum of the numbers in each of the two main diagonals is also 15. So a magic square is one where the row sums, the column sums, and the two diagonals have the same sum. Over the centuries, this particular pattern of numbers acquired great religious and mystic significance and appeared in many different forms, as you can see. Here, for example, the Chinese were very good at inventing magic squares. Here's a 9x9 magic square made from the numbers 1 to 81, so the rows and columns have the same sum, but this particular one has the property that if you divide it up, as you can see, a bit like Sudoku really, if you divide it up into the 3x3 squares, each of those 3x3 squares is itself a magic square. That was, I think, around the year 1100 AD or so. It was also possibly around this time that two classic Chinese texts appeared. One was the Zhubei Zhuangjing, the arithmetical classic of the gnomon and the circular paths of heaven. They always have lovely titles, these works. And this included a section proof of the Pythagorean theorem, or the Gugu, as they called it. And by rearranging the pieces, you can show that the square on the hypotenuse of one of the triangles is the sum of the squares on the other two sides. Another classic Chinese problem, which uses the Pythagorean theorem, and incidentally I say Pythagorean theorem, not Pythagoras' theorem, because there's really nothing historical that links it to Pythagoras. This is the broken bamboo problem. In this problem, you've got a bamboo, and you break it. It's originally 10 feet high, and you break it so that its upper end reaches the ground 3 feet from the stem. And you've got to find the height of the break. Now, in modern algebraic notation, which the Chinese didn't have, we can call the answer x, and the rest of the bamboo is y, so that x plus y equals 10. That's the length of the whole bamboo. And by the Pythagorean theorem, x squared plus 3 squared equals y squared. And if you combine these two equations, which is quite easy to do, you just write y equals 10 minus x and substitute, and the x squares cancel, which is nice, and that gives you the answer.
When does this proof date back to?
This sort of problem was looked at about, I think we're talking about 250 BC, that sort of time. That's when this problem was around. But it was around for many, many centuries. A lot of these problems did survive for many years. And things like the Gugu would probably have been started up a lot earlier than that as well. So some of you may have met the Chinese remainder theorem, so called because it apparently originated in China around 250 AD, when Sun Zi, in his modestly entitled Sun Zi Zhuangjing, Master Sun's Mathematical Manual, asked the following question. We have an unknown number of things. If we count them by threes, there are 2 left over. If we count them by 5s, there are 3 left over. If we count them by 7s, there are 2 left over. How many things are there? Many of you will have seen Marcus de Sautoy's television programs, The Story of Maths, which came out in 2008 and were repeatedly on television. And in those programs, and they're all on YouTube, so you can watch any of them. And I would strongly encourage you. There are 4 one-hour programs on the history of mathematics. And the first one has the Egyptian and Mesopotamian stuff and Greek material. The second one has China and India, and then into Europe and so on. And in the second one, he's in this Chinese market with this woman who is selling eggs, I don't know what she thought about it, but he started rearranging the eggs in rows of 3, and found there were 2 left over, and then rows of 5, and there were 3 left over, and so on. And so this is the problem. How many were there? The answer that Sunzi gave was 23, which certainly satisfies all of these results. If you count them by 3s, it's 21 plus 2, and so on. But Sunzi also provided a full explanation of how to solve this problem and any other of the same type. And so the smallest answer is 23, and Sunzi also indicated what the next answer was. To get the next answer, you just add 3 times 5 times 7, which is 105, and that gives you the answer. Now, the bamboo problem that we were talking about earlier appeared in the other great early text, the Zhujiang Suanshu, and I apologize to any Chinese people here about my pronunciation, because I don't really know how to pronounce them. It's usually called the 9 Chapters on the Mathematical Art, or something like that. This remarkable work contains 246 questions with answers, but with no working shown. And it may have been used as a textbook. It deals with both practical and theoretical matters. For example, there are problems from agriculture, business, surveying and engineering, and more theoretical things, discussions of the areas and volumes of geometrical shapes, the calculation of square roots and cube roots, the study of right-angled triangles, and the solution of simultaneous equations. And the last topic in particular is remarkable, and I'd like to show you an example which is not as complicated as it looks. There are 3 grades of paddy, or grain: top grade, medium, and low grade. And the first sentence says, if you take 3 bundles of top grade, 2 bundles of medium, and 1 bundle of low grade, that yields 39 measures. 2 of top, 3 of medium, and 1 of low leaves 34 measures, and 1 of top, 2 of medium, and 3 of low yield 26 measures. How many of each type are there? Now, these days, we would write down those 3 simultaneous equations that you can see there, and we'd solve them step by step using standard methods. Interestingly, the Chinese did exactly the same way. They wrote down on the right, they actually sort of would write them vertically rather than horizontally, but basically it's the same as we would do. And then they started manipulating them using a systematic method. And the amazing thing is that the method we use now to solve systems equations like this, which is often called Gaussian elimination, after the mathematician Gauss from around the early 1800s, and it gives the answer that we can see here. But that's exactly the same method, apart from being turned around, that the Chinese did. Their method is exactly the same as the one that Gauss gave some 2,000 years later, but Gauss got the credit. And this isn't the only time that the Chinese got there before anyone else, or most people. For example, the Chinese, some of you will know Pascal's triangle for binomial coefficients. Well, the Chinese certainly had a Pascal triangle 450 years before Pascal, although before that there were Arabic ones and Indian ones as well. The final Chinese topic I'd like to look at is the evaluation of pi, which is the ratio of a circle's circumference to its diameter. Around AD 100, Zhang Hong, inventor of the seismograph for measuring earthquakes, suggested the value square root of 10 for the answer. Now, the square root of 10 is about 3.16, pi is 3.14. It was really quite a good approximation, and one that was widely used not only in China but in India and various other places as well. So it's quite a good approximation. Correct value is about 3.14159. Now, Archimedes in Greece had actually approximated the value of pi by taking a circle, and to calculate its circumference, he put inside a hexagon. And he put a hexagon around the outside as well. He calculated the perimeters of the inside hexagon and the outside hexagon, and then the circumference of the circle, of course, would lie between them, and found out that it lay between 3 and about 3.464, I think. Not very good. He then double the number of sides. Instead of the hexagon, he took a dodecagon with 12 sides and did the same thing, and then doubled it to 24, 48, 96, and got the value. Well, Archimedes found that the value lay between 22/7, which is the one that we all know, a little less than that, and a little more than 3 and 10/71. So it lies between 3 and 10/71 and 3 and 10/70, which in our decimal notation gives you 3.14. Now, Liu Hui did a similar thing. He was actually concerned with areas, pi r squared rather than 2 pi r type formula. And he, as you can see, he surrounded the circle where he put the polygons inside, and he doubled the number of sides from 96 to 192, 384, and so on, all the way up to 3,072 sides. He didn't draw it, of course, but he did the calculations, and he got that value 3.14159. But the really remarkable result was of Zhu Zhongji and his son around AD 500, who continued doubling up to 24,576 sides, did the calculations, and got a value of pi, which in our decimal notation is correct to 6 decimal places. And he also had the approximation, we know 22/7, he also found 355/113, which does give pi to 6 decimal places, and that particular approximation wasn't discovered in Europe for another 1,000 years. We'll now return briefly to Indian mathematics, concentrating on just two mathematicians, Aryabhata and Brahma Gupta. Aryabhata was about AD 500, as you can see, and he's not in a snowstorm, he's just admiring the stars in the sky. One of Aryabhata's main contributions was to sum arithmetic progressions, such as 6 plus 9 plus 12 plus 15 plus 18 plus 21. Arithmetic progressions means you go up by the same amount each time. Here are 3. And how do you add these up? Well, he gave the answer in 2 forms. The first one was in words. It's quite easy. You just take the desired number of terms minus 1 halved multiplied by the common difference between the terms plus the first term is the middle term. This multiplied by the number of terms desired is the sum of the desired number of terms. So that's how to do that. A slightly easier formulation is you take the sum of the first and last terms and then multiply that by half the number of terms. So you take 6 plus 21, that's 27. Half the number of terms is 3. And if you multiply those, you get 81, which is the correct answer. And you also get the correct answer from here, actually, the middle term. You take the desired number of terms, that's 6 minus 1 and 5. Halve that 5 halves. Multiply by 3 gives you the middle term, which is interpreted as 13 and a half. And then you multiply that by 6, and that gives you 81 as before. We use these formulae here, and this first description gives you that exactly, and the second one gives you that. So it's what students will use now. But it's although that's rather indigestible, this actually does give you a general rule for summing these arithmetic progressions. The other person was Brahma Gupta, who was a bit later, 100 years later, and he gave rules for calculating with 0, which he also called cipher or naught. And also not only 0, but also negative numbers as well. Now, 0 had 2 purposes. It was used as a placeholder that you used for distinguishing between, say, 35 and 305. The Egyptians would have actually left a gap in the sand, or they'd put in a sort of pebble or something to indicate that there's a 0 there. That represented 0. But it's also a number that you calculate with. And how do you calculate it? Brahma Gupta gave you the rules. So if you take cipher and negative, in other words, if you add 0 to a negative number, you get a negative number. Positive plus 0 is a positive number. 0 plus 0 is 0. Similar things for negative. If you take a negative number from 0, you get a positive number, and the other way around. Then you get the product of cipher and positive. That's 0 times the positive number, or 0 times the negative number is naught, is 0. 0 times 0 is 0. And so these are instructions for how to deal with this. The interesting thing is the last one. Cipher divided by cipher is naught. Well, 0 over 0 can actually take any value you like. It's a meaningless expression. And it was actually some centuries before mathematicians really learned how to deal with dividing by zero. But it's interesting that that statement does actually appear in Brahma Gupta's writings around 600. One more Indian topic, and then we'll go on to the Mayans. So Brahma Gupta and a later mathematician called Basara also worked extensively on a particular equation now known wrongly as Pell's equation. Pell was a mathematician around 1700, and Euler called this Pell's equation when it wasn't. They asked questions of the form, well, tell me, O mathematician, I love the way they phrase these, what is that square which multiplied by 8 becomes together with unity a square? In our algebraic notation, if it's x, 8x squared plus 1 is a perfect square. Well, it's easy to find some solutions by inspection. If you take x to be 1, then you get 8 plus 1 is 9, which is 3 squared. Or if you take x to be 6, then you get 8 times 48, which is 288 plus 1, which is 299, which is 17 squared. Whereas other numbers, if you take x to be 2, you get 33, which is not a square. So you've got to look for solutions. So that's one particular example. More generally, you can take any number here, other than a square, and see if you can find some solutions. And the hardest ones were 67, x squared plus 1 equals y squared, and 61. And it's quite remarkable that, I think it was probably Basara around the 1100s, looked at this and he managed to come out with this solution. This is the smallest solution. How on earth did he get 5,967 for x and that for y? It must have taken, well, he must have had some method, but we don't know what it was. And it's really quite remarkable. One thing I would like to point out is, in fact, they also described a method for finding new solutions from old ones. And this is rather pretty. And those mathematicians among you might like to try and explain why it works. So supposing, let's come back to this one. Suppose you've got x is 1 and y is 3. So you put 1, 3. And because you haven't got any other solutions, you put 1, 3 again. You then say 1 times 3 is 3. This is cross multiplication. 1 times 3 is 3. Add 3 and 3, you get 6. That's another solution. Now you've got two solutions. You've got 1, 3, you've got 6, 17. So you look at 1 times 17 is 17, 6 times 3 is 18, add them together, 35. And if you take 8 times 35 squared plus 1, then you get 99 squared. And you can deduce, as far as you want, you can find infinitely many solutions of this. Before leaving India, I'd just like to mention a later development, the wonderful observatories known as Jantar Mantar in Delhi and in Jaipur. And these contain massive astronomical instruments that were used for measuring the heavens to an amazing degree of accuracy. Well, we come now to our final culture, the Mayans of Central America. There's been a Mayan culture for many thousands of years. Indeed, it still exists. But the heyday of their mathematical activities was focused around the period from about 300 to 900 AD. The Mayans were situated over a large area centered around Guatemala and present-day Belize, and extending from the Yucatan Peninsula of Mexico in the north to Honduras in the south. And we have primary sources in the form of some stone columns called stelae and a handful of codices. But regrettably, most of the codices were destroyed by the Spanish conquerors who arrived in this area after the year 1500. But the best-known codex is the 12th century Dresden Codex, so called because it now resides in Dresden in Germany. I have seen it, it's a wonderful, wonderful thing. And there are a couple of other surviving codices, such as the Madrid Codex. This is actually the Madrid one here. It was drawn on a 22-foot length of paper made of tree bark and folded, and was intended to guide Mayan priests in ritual ceremonies involving such pursuits as hunting, planting, and rainmaking. And the things to concentrate on here are the symbols consisting of lines with dots over them. These are the Mayan numerals. So notice these ones in particular. We're going to look at this one in a minute. Here you can see the numerals more clearly. The Mayans essentially used a dot representing 1 and a line representing 5, and this table gives the numbers up to 19 obtained by combining them. 1, 2, 3, 4, 5, 5 and 1, 5 and 2, and so on. You can also see they had a special symbol for 0, looking rather like an eye. The Mayans essentially used a number system based on 20, and so got larger and larger numbers by combining these ones. For example, the symbol at the top, which we saw on the previous slide, has 13 below 12, and that means 13 ones combined with 12 20s, which is our 253. One rather jolly feature of the Mayan numerals is that there's an alternative form for each number, the head form, which you can see in the middle. These can vary a bit, but 0 always has clasped hands across the lower part of the face, while 3 has a banded headdress. And these head forms appear on various columns, such as the one on the right, which can be interpreted to give the date when it was constructed, as we'll see. So you can see that each of these head forms there, these heads, represents one of these numbers, which represents one of these numbers. And by combining them, you get these rather nice patterns. Now, the Mayans had a fixation on the calendar, and they had essentially two different kinds which they combined in order to keep track of the passage of time. The first was the ritual calendar of 260 days, known as the Tzolk'in, consisting of 13 months of 20 days. And we can think of it as two circular wheels that you can see here, with the 13 months on the top one and the 20 days on the bottom one. And each day had a number and a name, such as 1 emix. You can see 1 is linking up with emix. Now the next number is not 2 emix. What you do is you rotate them, and then 1 goes next to emix, and 2 goes next to ik, and then 3 akbal, 4, and so on. And so they rotate like that, and this gives them all their numbers with 260 in total. The other calendar has 18 months of 20 days, plus an extra 5 inauspicious or evil days to make up the usual 365. And heaven help you if anything goes wrong on any of those 5 days. And these two calendars operated independently, but was also combined to give a long count, or calendar round, in which the number of days was the least common multiple of 260 and 365, which you've immediately worked out as 18,980, or 52 calendar years. So that was another unit of time. The long count was 52 calendar years. For example, the day of 4 Ahu and 8 Kumku won't come around again for 52 years. And these periods of 52 years were then packaged up into even longer time periods, which were due to come to an end in December 2012, when the world would end. But it didn't, which is why I'm giving this lecture. I mentioned that the Mayans based their number system on 20, which is almost correct. But since their number system was used mainly for keeping track of the calendar, they made a slight modification to take account of the number of days in the year. So they introduced an 18 into their 20-based system to give 360, which more closely approximated the number of days in a calendar year than 400 would have done. So their units were based on the following scheme. 1 kin was 1 day, 20 kins, or 1 uinil, don't know how to pronounce these, was 20 days, 18 uinils is 1 tun, is 360 days, 20 tons, 1 katun, that should be 7,200 days there, and then 20 katuns, 1 baktun is 144,000 days. They had no problems with calculating with such large numbers. And here on the right is the largest number ever found on a codex. Starting at the bottom, we have 1 15 20s, 13 360s, 14 7200s, and so on. And doing the calculations, as shown on the right, and adding the results, gives the grand total of 12,489,781 days, or over 34,000 years. So I'd like to conclude with a limestone calendar stone that features a particular date, possibly an important festival, or possibly just the date that the stone was constructed. The monkey on the second picture on the right, you can see the monkey. That represents day, and the god's head above its hand and representing the sky represents 6, while the head below it means 10. So this picture apparently represents 16 days. And if we similarly interpret all the pictures here, add them all up, and then add the result to the official Mayan starting date of 3114 BC, we obtain, what do we obtain? The exact date of this stone, 11th of February in the year 526 AD, which is quite remarkable and is a nice thing to end with. Thank you very much.
Thank you very much, Robin. Plenty of time for questions. Gentlemen.
Yes.
Can you wait for the microphone?
Thank you very much. What was just something that was written for this concept of zero. If I understand, that came first from Indian mathematics. We didn't have Roman numerals, and then it was handed over to the Arabs who gave it to Europe. Can you just say if I'm correct and elaborate on that?
Yes, that's right. We don't really know when zero first came, but it was certainly India, probably around the year 400 AD. If you watch the Marcus de Sotoy programs, you'll see that he goes into a cave in Gwalior, which has the symbol marked down. But that was about 700 AD, 7 or 800 AD, and it's now, and that was believed to be the earliest, actually one that printed, actually there are now known to be earlier ones than that. But somewhere in that period, 400 to 800 AD, the zero symbol started to appear. It was a circular symbol, meaning cipher, or zero. It corresponded to sort of making a hole in the sand, and so on. The word sifra, that's basically what it means, I think. So that was the period that zero came, and then when the Islamic mathematics started with the new religion, Islamic religion coming in around the year 750 or so, Baghdad was on the trade routes from Europe and from the Greek world, if you like, or well, the Greek world didn't exist then, but the Greek and Roman culture went along the trade routes. The trade routes didn't only deal with silks and spices, but it dealt with manuscripts and books and so on, and they came from the Greek and Roman culture came from the West, and the Indian culture came from the East, and in Baghdad, they had this group of people called the House of Wisdom, where they actually sort of took all these things, they developed them, they translated them into Arabic and Persian and other languages, and they developed them and made them their own. And then eventually the Islamic world went across northern Africa, up into Europe, into southern Spain and Italy, and everything got translated into Latin, which then became known in Europe. So there are all these different things going on, but it was the Ashoka columns with the first numbers, if you like, of the Hindu numerals. Then the zero came in, and then the Islamic scholars took it over and developed it. So that's why we call them the Hindu-Arabic numerals. Yes. Just behind you, yes.
Yes. The microphone is coming. Yes, go ahead, please.
Thank you very much for your talk. Did any of these cultures have lotteries? And was there mathematics associated with that?
That's a very good... I've never heard that question before.
Only just occurred to me.
I haven't the least idea. Norman, do you know the answer?
Yes, they did.
They did? Okay, Norman would like to answer the question. Norman and I are teaching this history of maths course together, and he knows everything, so he'll...
Certainly in Greek and Roman times there were lotteries, and I think there is evidence from the earlier civilizations as well, the Egyptians and the Mesopotamians. Throwing dice was or a version of the dice was the main pastime, and there are an awful lot of references to that in both Greek and Roman literature.
How about the non-Western cultures?
That is getting into the question of the attitude of the people to predestination, the belief in the gods having ordained everything and so forth. And I'm afraid I'm not an expert.
But I should say that Norman has a wonderful book coming out shortly called Quite Right, which is about the mathematics of measurement and of money, and that will be coming out in the next month or two. Yes.
What is Norman's other name?
Norman Biggs.
Well, we'll be on our we'll be online on our Twitter feed. So, okay, I saw Bernard.
So the unit fractions of the Egyptians are not as weird as they seem. So I like to introduce them to say, if you have 5 pieces of bread and want to distribute among the 7 people, well, cut them in half first. Then you have 10 pieces, and then you have 3 remaining that you cut then into thirds, and so on. Is that also clear that this is the origin of this unit
Yes,
fraction?
I'm sure that's the case. We tend to think, well, we do our fractions our way, and we tend to think that, aren't they strange doing it their way? And they would think exactly the same about what we do. As you say, they would sort of cut things up into 6, if you like, and then they cut the 6 up into smaller ones and so on. And that's illustrated on the first of Marcus de Soto's programs. He actually does that, dividing up a cake or something like in that way, and then combining them together. So, for example, if you combine a third and a sixth, you'll get a half, and so on. So, yes, that's right. So it's very easy for us to think how primitive they were, what a strange way they did of doing things. But it's very important to try and look at things from their point of view in the culture of the time, rather than with our hindsight. So there's
There's a lady there in the back, please.
Thank you very much for your talk. I was wondering, to what extent do you think that if some of these civilizations wouldn't have been destroyed, there would have been some sort of convergence into some very sophisticated mathematics? Also, to what extent would it be similar to our mathematics currently? Thank you.
I'm not really quite sure how to answer that. I mean, a lot of things were destroyed, of course. I mean, a lot of our primary sources have been destroyed. Not only have they disappeared, but the Greek culture, of course, the various libraries were with earthquakes and fires and things, they all disappeared. I don't think that really answers your question. I'm not really quite sure how to answer your question, I'm afraid.
I think the question, Robin, as I understood it, is what suppose if the Mayans or kind of would have kept on developing, would their mathematics be converging to what we think is now modern mathematics?
Sorry.
Would it be merged to kind of... I think that's I understood.
Oh, sorry, okay.
I mean, I had a similar kind of question, kind of what would be a dominant one if they all would have been kind of...
I don't think there's any way that we can know. I mean, a lot of... in some sense, you know, most of our mathematics as we know it now has its origins in the Greeks. Certainly, the whole idea of Greek mathematics, the fundamental idea there is the idea of proof and of logical deduction and so on. So the Greeks developed the idea of proof, and you prove things by step by step you've got a set of axioms, and you prove some simple results, and more complicated ones, you get this huge hierarchy of results with everything depending on everything below. And basically it was the Greek system that led to what happened then in the Islamic world. Of course, when they got there, that was developed and then came into Europe and so on. I don't know how much. Certainly, if the Chinese, all their discoveries, if they had merged with the Greeks and so on, then of course a lot more would have been done, because, as I say, you know, the Chinese discovered things like solving simultaneous equations and so on. So all these different things they had different things to offer, and even things like the Hindu-Arabic numerals, the way that they developed by the sharing of Indian ideas with Islamic ideas and so on. But we really don't know very much about how much they did combine. I mean, how much did Indians and Chinese mathematicians know about each other? And how much did the Greeks know about Mesopotamian and Egyptian mathematics? And you know, the various things have been written, but there's an awful lot that's not really known. You know, where did the Greeks get their idea of proof from? It's said that Pythagoras, I think, had been to Egypt or something, but you know, we don't really know, and we don't know what he would have picked up from there. Another one at the back. The one at the back, and then
the one a little bit too. Yeah, that one was first. One back. Yes, and then we go to the second.
Yes, sorry. I'm reminded just of an anecdote about Gauss that we're told that he was told by his maths teacher when he was quite young to add all the numbers from 1 to 500 and then used the formula for arithmetic progressions and amazed his maths teacher by accurately calculating all the numbers in less than an hour. And you mentioned that in 500 AD there was already an idea of how to solve arithmetic the sum of arithmetic progressions. So how possible is it that Gauss, of course he was a genius, but how possible is it that he had perhaps already heard of it? Is there any evidence of that having been over?
A, there's no foundation for the story. Secondly, even if there were, it was 100, not 500. And I'm sure the way he would have done it, if he did, was to say 1 and 100 is 101, 2 and 99 is 101. 3, so you've got these sort of 50, 101s, which gives you 50-50 straight away. So you don't need a formula. You just, you know, as I say, I'm sure he just did it that sort of way, which would have come quite naturally to someone clever like him. But he probably didn't do it anyway.
Okay, question in the back.
Hiya, thank you for your talk. I have kind of a follow-up question to the lady in front of me who asked the question. I was wondering, I don't know if you know, if there are any instances where Western mathematics kind of lacks and doesn't provide us with solutions, and we kind of have to resort to non-Western methods of solving a problem.
Not well. I mean, as I say, are you talking about now, or well, now? I mean, mathematics is completely worldwide, and everyone collaborates with everyone. If I were writing a paper on something and I found that someone in China or in Mexico or something like that were doing the same thing, we would actually collaborate. So there's complete international communication. Sorry? Well, I think all methods are pretty international now. I mean, I don't think there are national ways of doing mathematics very much anymore. I mean, there have obviously been some countries which concentrate on certain areas. I mean, the Poles concentrated a lot on topology and analysis. The Hungarians did a lot on number theory and combinatorics and so on. So there are these national specializations, if you like, but everything is completely worldwide. What is interesting is that, of course, as I said, you know, the Chinese had Pascal's triangle 450 years before Pascal, and Islamic mathematicians had it even earlier. So if there had been a lot more collaboration then of course a lot of these things would have developed a lot earlier, or wouldn't have been rediscovered in the West, who, as I say, didn't know what had already happened in non-Western countries.
Okay, question here in the front.
And then there's one up there after that.
Sorry, Mr.
Thanks for the talk. Do we know what was the profile of a mathematician in these civilizations? Were they the religious people? Were they bankers, the traders? And what was their social status?
We know really rather little about an awful lot of them. As I say, the people that would have read the Egyptian ones were scribes. We know that they were the educated people, and they were being taught by these papyruses and these clay tablets and so on, learned to write, so that they could write for for their they were the scholars. We don't know very much about individual people. scribe that wrote the Rhine Papyrus was called Armies. We know that because he actually signed it. But by and large, we don't know about individuals, except, as I say, that certain people that did sign their names. I mean, we saw Master Sun's manual, the Chinese one where he did the Chinese remainder theorem. So there we actually know a bit about him. But I don't think we know much about his life and everything like this.
There was a question at the back first, kind of, and then we go.
No,
Yes. Yeah, I'll go for you.
So if we assume that at least two of these systems of mathematics really did emerge isolated without any influence, what extent do you think they're actually innate? What aspects of mathematics would be innate? Just basic arithmetics, or also forms of geometry and algebra and calculus? So how, I guess, do you distinguish between what aspects are through culture and what aspects would actually be innate if they're really emerging isolated?
Well, I mean, some of these are actually to fulfill a need. In Egypt, of course, they needed to find the areas of fields, and they needed to work out payment of money, and they paid their slaves in bread and beer and everything, so they needed to do calculations which involved things like that. So some of them were sort of, there's a question about irrigation of the land. The Nile flooded every year, and so this brought in all sorts of mathematical problems about food and about money and all sorts of things. So a lot of it was a desire to deal with practical problems, whereas some of them, of course, were very impractical. You know, the Greek idea of proof was not to solve practical problems as such. But Plato, for example, when he wrote the Republic, he actually, in Plato's Academy, and incidentally Academy, the word Academy comes because the Academy is the name of a suburb of Athens, and which is where it was placed. So in 387, when Plato's Academy was started, he had a strong emphasis on the four mathematical arts of arithmetic, geometry, astronomy, and music, the so-called quadrivium. He felt these were the important things for the ruler of the state. Greece had a whole lot of city-states, and he felt that the rulers of these states needed to know mathematics, just like our current political leaders. They're all excellent at mathematics. Or if they were, of course, the world would be in a so much better place. And Plato had the right idea. He felt that if they knew the mathematical quadrivium, if you like, that would enhance the way they ruled the state. So a lot of these things are based very much on, and there are long discussions in Plato about what is the use of mathematics, what's the use of geometry, and so on. So mind you, some of this is quite controversial. I mean, the Egyptian Rhine Papyrus, for a long time, some people thought they were practical problems, because if you find in the Rhine Papyrus, you find the volume of a cylindrical granary, or you've got a circular granary of a certain height. What's its volume? That looks like a practical problem. And you're sharing out loaves of bread among 13 people so that 3 of them get double rations and the rest get single rations. How much does each one get? Those sound practical problems, but the answers they had with all this long string of unit fractions, now that wouldn't have been practical. So some of these problems we don't really know, but we believe they were used for educational purposes, but they were set in a practical context to make them look more relevant, just like today's textbooks where you have things set in a so-called practical setting to make them seem more relevant. But I won't get into that.
Okay. I think yes.
Just a quick question. Do you know the particular use of the 12 million days in the Mayan, like the largest Mayan number you found, what it was used for?
Not really, no. I don't know that they knew what it was used for, but they just loved calculating these things. I mean, obviously, as I say, they had these long... They did have this long view. If it started in 3114 BC, they actually certainly calculated as far as 2012. So that was their time scale that they based on. They didn't think anything went beyond there.
It might have been about the stars, because they're very keen on stars.
Oh, yeah, that's a good point. Yes, that's a very good point.
In fact, they used to make children, small children, they used to put stones in front in their foreheads, so that they would be squinting,
Oh.
so that when they could look at the stars, they would have a clearer view.
Oh, that's very interesting. Thank you for that. Yes.
Okay.
Right.
We had a question. Sorry, there was a lady there.
And we all get pretty starry-eyed when we looked at those Mayan numerals.
That one there in the middle. I think that was the next one. And that was a few hands.
Thank you for the talk. Do we know of any civilizations that had a counting system that wasn't of the base 1 to 9 or 9th base?
Well, they're all based on well, I mean, in some sense, they all had 1 to 9 in there. You know, the Mesopotamians used 60, and a lot of North American Indians used different scales. They used scales certainly on. They're all based essentially on 5s and 10s and things. Some of them were based on 20, as we saw. Some were based on 10. I mean, even 20 still exists in English. Well, in the olden days, we used to say 70 years and 10. French still have 80. For 80, they have 420s. So there's still a bit of 20 surviving in some of these. But I don't know of any particular ones where they had weird numbers. Although, as I say, some of the North American Indian tribes, I think they use some quite unusual ones. I know an article, I must reread it sometime, but that's, so that there might be some, but as I say, most people tended to use things based on fingers and toes.
Okay, I saw a hand in the far corner. Far right. Yep. Thank you.
Yeah, you was mentioning about almost the necessity. Invention is the mother of necessity in terms of developing mathematical process to count grain on areas of land. Thinking of Tim Berners-Lee and his sort of invention with the internet at CERN in order to communicate quicker with fellow scientists. Do you have any personal knowledge or insight into that sort of area of discovery, which seems to be so profound and so recent in terms of the Western industrial society in relation to his love of working and developing codes? And do you know any of the maths behind that at all?
Well, I think that's really a bit out of today's topic. I'm not really quite sure what to answer to that. Can you? I don't really think I really quite latch onto that question. So, one thing which I would like to say, incidentally, about things is that, you know, the Greeks, as I said, they were interested in proof, and they were concerned with whether things were true or not. They certainly weren't concerned with practical uses. For example, in Euclid's Elements, you'll find a proof that there are infinitely many prime numbers, and the Greeks were very interested in prime numbers, and they had perfect numbers where if you add up all the factors, you get the original number. 6 has factors 1, 2, and 3, which add up to 6. 28 has 1, 2, 4, 7, and 14, which add up to 28. And next one to 496, and 8, 1, 2, 8. And then there's another one till my favourite number, 33,550,336, where its factors add up to that number. Well, there's nothing practical about that. But this is the art side of mathematics, if you like. Mathematics is fun. Mathematics you do because you're interested. Prime numbers. There would be prime numbers in any culture whatsoever. You know, on Mars, if there are any characters there, the basic idea of a prime number will still exist, whatever number systems you have. And prime numbers really were done for the fun of it, you know, and what are their properties. Some questions you can ask are so easy to ask, but we don't know the answer. Can every even number be written as the sum of 2 primes? Goldbach's conjecture. Well, it's easy to check, isn't it? That 8 is 5 plus 3 and 10 is 5 plus 5 and so on. And you can check up to 4,000 million. But that might just be coincidence. And in mathematics, unlike science, truth, it has to be absolute. proof has to be absolute. It has to work in every case. I mean, I'm not getting at engineers when I say, when they check primes, they say, well, 3 is prime, and 5 is prime, and 7 is prime, and 9 is experimental error, and 11 is prime, and 13 is prime. I'm not getting at it. But there cannot be any exceptions, okay? So prime numbers are basically, for 2,000 years, were done out of the interest. No practical applications at all. Now, of course, there's cryptography. And there's your credit card, the nation's defense. They all depend on number theory of Fermat, a result of Fermat. The security of everything in the world depends on some quite simple results in number theory, which, of course, no knowledge of these was had by the Greeks or Fermat or even more modern number theorists like Hardy, who did wonderful things in prime number theory, but he was always seemed to be quite proud that it had no applications. Well, he certainly, he didn't know of any, and he didn't care whether it had any or not. Now, of course, number theory is absolutely crucial in our everyday life. Yes, there's one at the back.
There's one question.
Thank you very much. You said that the Mesopotamians, they used mainly clay, and the Egyptians papyrus or paper or whatever, and that the paper didn't survive.
Papyrus is a sort of reed.
Yeah. Reed seems to be much more practical in terms of distributing it and using it on an everyday basis, and sort of putting something into clay. I mean, there's very little I would want to put into clay of what I come up with. So, do we know why one group did this and the other that? Is it because they only had clay, or is it because
it depends on what you have. I mean, the Egyptians had a lot of, because of the Nile, they had a lot of reeds, and they found that they could write on that quite well. You saw some examples, some bits of the Rhine papyrus here, and they found that was a good way of writing things, and you know, for everyday life that would have been fine. We write on paper, but the paper we write on, I mean, most of those pieces of paper are not going to be around hundreds of years from now, and so paper doesn't survive. And the thing about clay is they used a lot of clay, and with the stylus you could actually write, and you know, they really, as I say, they managed to write very detailed stuff on these. And they baked them in the sun, so they were always there. And as I say, those have survived the centuries in a way that reeds don't. So I think it was the material that they had available, and that's what they used. If the Mesopotamians had had papyrus, they might have used it. Fortunately, they didn't. But the Greeks, of course, used papyrus, which is why we have virtually no Greek primary sources.
Okay, I see a hand here, a hand there. I think we should call it the final two questions. This one first was already there, and then the gentleman there.
Hi. I was just wondering if the multiple mathematical principles were discovered in these traditions, why are they not properly credited sort of today within Western tradition?
Credited to
as in the things like Pythagoras' theorem being discovered much earlier.
Well, we don't know who discovered it. It was certainly, and the Pythagorean theorem was certainly known. The result was about right-angled triangles, was certainly known to the Mesopotamians 1,000 years earlier. We don't even know whether Pythagoras existed. He probably did. But we certainly know that he had a school. And the belief is that, for that particular example, that it was the Pythagorean school. I mean, the result had been known for hundreds of years. But it was the Pythagorean school that probably came up with the first proof. The proof given in Euclid is quite complicated. It might have had a dissection proof, a bit like the Chinese ones, for example. I mean, Pascal's triangle, we call Pascal's triangle because Pascal actually wrote quite extensively about it, and there are different approaches to Pascal's triangle. You can regard it as, well, you can regard it in three different ways, essentially, and Pascal pulled them all together and wrote about them and tied them together. But in fact, there's a Chinese one, and there was, and the earliest Pascal triangle I know was Al-Karaji in 1007, which is an Arabic one, and I think there are Indian ones as well, and there's certainly quite a lot of European ones. Cardano and Tartaglia, who solved cubic equations, for example, they all had Pascal triangles. And it's just chance, I suppose, that it's called after Pascal, even though other people had it earlier. Didn't someone say that there's a rule that everything is named after the wrong person? And the person who's credited with that rule, that was the wrong person too. Yes. So I mean, a lot of things we do know who came up with them, but in many cases, there are results. The Bernoulli numbers called after Bernoulli because he published them, but they were known 100 years earlier by someone called Faulhaber, and there are all sorts of these different things. And later on, we found that someone else has discovered them first. Galileo is often given credit for being the first to use the telescope, but Thomas Harriot, got there a few months earlier. But once the idea was established that this person did it, that tends to stick. And even if we found that someone earlier did it, it's very difficult to try and change things at that stage.
Okay, there was one question there.
Thank you. When did we see the emergence of mathematical objects other than numbers?
Sorry, when do we?
When did we see the emergence of mathematical objects other than numbers?
From the very beginning. These days, people talk about maths at school, learning tables, because everyone tends to forget, it's regard mathematics meaning numeracy or arithmetic. But geometry started just as early. Algebra was much later. Algebra didn't start until the Islamic mathematicians, in fact, Al-Khwarizmi. Al-Khwarizmi wrote a book on arithmetic, and the word algorithm is named after Al-Khwarizmi, although my American friends tell me that the word algorithm comes from Al Gore, but there we are, I don't believe it. But he also wrote a book where one of the words in the title was algebra. So that's an area of mathematics which came later. But from the very beginning, you had arithmetic because, of course, you had to deal with everyday accounts like money and everything like this. And you'll learn about that if you read Norman's book when it comes out. But just as much, they had to measure fields. And so geometry, the mathematics of space, has got just as older history. And of course, as you were saying, there's astronomy as well. There's not only the world around us, but there's the world above us. So ideas of space and ideas of number both developed from very earliest times.
Okay, well, thank you very much, Robin, for a very...